In this video, we'll introduce the concept of absolute and conditional convergence, which is part of section 11.6 in Stewart's book. We won't cover all of 11.6 in this series of videos. We'll do some of it in the next series, but I wanted to give an introduction to this really important concept that's related to the material about alternating series that we've been talking about. So this idea is best illustrated with an example. So let's consider the sequence given by an equals -1 to the n minus 1 over n squared. So what does this look like? We get 1 for n equals 1, then -1 over 4, then +1 over 9, then -1 over 16, +1 over 25. The denominators are squares, and they alternate plus, minus, plus, minus, plus, minus. So if we make a series out of this sequence, this converges by the alternating series test. We just have to check, in this case, our Bn equals 1 over n squared, and this is decreasing. And the limit, as n goes to infinity, of Bn equals 0. So this converges. But we know more. That if we define a related series, S plus, where the only difference is going to be, instead of taking a sum from n equals 1 to infinity of an, we put in absolute values. We take the sum from 1 equal to infinity of absolute value of an, then what is this series? This is a sum from n equals 1 to infinity of 1 over n squared. Because the only thing the absolute value does to an is it takes this -1 to the n minus 1 and turns it into 1. Since it's always +1 minus 1, +1 minus 1, +1 minus 1, all the minus ones get turned into 1s by the absolute value. And S plus, this also converges because this is a p series with p equals 2. So the point is that S converges even when you put in absolute value signs. And this is the beginning of the idea of absolute and conditional convergence. Absolute value signs. Okay, so let me give a definition. Let's say S is equal to a sum from n equals 1 to infinity of an. This series S is absolutely convergent if this series S plus that you get by taking a sum from 1 to infinity of an, but with absolute value signs, converges. Okay, so that's the important new definition, that absolutely convergent means that your series converges even with the absolute value signs. So S is conditionally convergent if S converges, but S plus diverges. So what have we seen? We've seen that this first series, the sum from n equals 1 to infinity of -1 to the n minus 1 over n squared, is absolutely convergent because S plus converges. This series is our first example of a series that's absolutely convergent. So I'm going to pause and erase, and then we'll see several more examples. Before we talk about this next example, let me just highlight an important fact. We have two related series, S and the series S plus, that we get by putting in absolute values. Absolutely convergent means that S plus converges. Conditionally convergent means that S converges, but S plus diverges. So just to clarify the relationship between S converging and S plus converging, it's not so difficult to show that if S plus converges, if you put in absolute values and you get something that converges, then your original series automatically converged. So absolutely convergent means that S plus converges, but that means that S also converges. So the options here are both converge for absolutely convergent, or S converges and S plus diverges. It's just not possible for S plus to converge and S to diverge. Okay, so let's look at this example. We have this series which comes from n equals 1 to infinity of minus 1 to the n plus 1 times 1 over n. And we saw that this converges. By using the alternating series test. But we know that if this series is S, then S plus is the sum from n equals 1 to infinity of minus 1, n plus 1, 1 over n, absolute value. And all the absolute value does is it replaces all these minus 1 to the n plus 1s with 1. So we just get 1 over n. And this diverges because this is a p series with p equals 1. So this series, S, converges, but S plus diverges. So S is conditionally convergent. So the first example that we talked about from this video was absolutely convergent, and this one is conditionally convergent. Okay, I'm going to pause and erase, and then I want to draw a picture that I think is really helpful in understanding the relationship between when a series converges, when a series S converges, and when S plus converges. Let's think about the picture of the universe of all series. If you have a series, maybe it converges, maybe it diverges. We know lots of examples of series that diverge. Something like a sum from n equals 1 to infinity of 1 over n, p series with p equals 1. That's just one example. But then with series that are convergent, they come in two types. There are the ones that are absolutely convergent, the ones that still converge when you put in absolute value signs. So something like minus 1 to the n over n squared. That's a series that's absolutely convergent. It converges, and S plus, the series with the absolute value signs, also converges. And then we have series that are convergent but not absolutely convergent, the ones that are conditionally convergent, like minus 1 to the n over n. This we saw converged by the alternating series test, but when you put in the absolute value signs, now you get a series that diverges. So a really common type of exam question that you would see is, here is a series. Is it divergent, conditionally convergent, or absolutely convergent? Those are the three options. So the first thing to check is check whether your series converges. If it diverges, you're done. If it converges, then you want to check, does S plus also converge? Okay, so let's look at one more example in this video. Let's take S to be a sum from n equals 1 to infinity of minus 1 to the n minus 1 over 5 times n minus 1. And the question we want to answer is this series absolutely convergent, conditionally convergent, or divergent? Okay, so looking at a series like this, what's the first thing you would want to try? Well, this is an alternating series because of this -1 to the n minus 1. So we want to apply the alternating series test with Bn equals 1 over 5n minus 1. If you look at the first few values of Bn, you get 1 over 5 minus 1 is 1 over 4, 1 over 9, 1 over 14. Bn is decreasing. All you have to do is check that the denominator is increasing. And the limit as n goes to infinity of Bn is 0. Because the denominator is getting larger and larger and larger, and the numerator is just 1. So S converges by the alternating series test. OK, so which case are we in? We can take this divergent possibility and throw it out. And now we just need to know, is S absolutely convergent or conditionally convergent? And that is the same as asking, does the series S plus a sum n equals 1 to infinity of 1 over 5 n minus 1 converge or diverge? If this series converges, then S is absolutely convergent. If this series diverges, then S is conditionally convergent. OK, so now we have to use one of the series tests that we know from before. Let's say that this is an. And we can take Bn equals something really, really close to this, 1 over 5n. Because now the limit as n goes to infinity of an over Bn is the limit as n goes to infinity of 5n over 5n minus 1. And this is 1. So what this tells us is either both series converge or both series diverge by the limit comparison test. So let me just write this here because we're almost done. We know that the sum n equals 1 infinity of Bn, this is a sum n equals 1 infinity 1 over 5n. That's 1/5 times the sum n equals 1 infinity 1 over n. But this series diverges because this is a p series with p equals 1. So the Bn series diverges, which means the an series also diverges by the limit comparison test. I'm just going to erase and quickly write the conclusion here. And we'll say that S plus diverges by the limit comparison test. So S, this series here, belongs in this piece. S is conditionally convergent, meaning S converges, but S plus diverges. So in the next and final video of this set, we'll just see a couple more examples of looking at a series and telling whether it's absolutely convergent, conditionally convergent, or divergent.